in the quant section. We're moving away from rates of return and applying the time value of money, and we're moving more on towards the more statistical side of things. So this module sees us moving into basic statistics, which we can then use later on for things like estimation, inference, and hypothesis testing. So in terms of the hit list here for the things that you need to know, we need to know about our different averages, some of which there's some ideas that we've mentioned before. So I'm not going to talk about trimming and Windsorizing because they were spoken about in the first module. But we'll talk about medians and modes. You need to know the difference between those. And probably the most important area in this section is actually standard deviation and variance, because that's the measure for risk, which the curriculum and texts in general pick up and run with when it comes to risk, the risk side of things. We tend to use these measures of central tendency, these averages, as reward when we're thinking about portfolio management and so on. This is our reward, and standard deviation, the level of dispersion around that expected return, is our level of risk. Right, so first up here we'll talk about the median. By the way, we have already discussed the arithmetic mean in an earlier module, so we'll skip that. Let's talk about the median here. Median, I always think median sounds a bit like middle. All right, so median, middle, that's what it's telling you. If you rank your data from lowest to highest, and then you pick the middle one, the value of that item is the median value of the data points, of the data set. It is the midpoint. All right. If you've got an odd number of observations, you can easily identify the middle one. You can actually add 1 to the number of observations, divide by 2. For example, here we've got 1, 2, 3, 4, 5 observations. Add 1 to 5, you'll get 6. Divide by 2, pick the third one. That's the ranking. Okay, you've got 2 to the left, 2 to the right, so the median is 7. If you've got an even number of observations, then the median is not so straightforward, but it's still not complex. Take the 2 middle items, so it's 9 and 10 that are in the middle here, and average those two. All right, so the average of 9 and 10, of course, is 9.5. Okay, the thing we need to know about the median is that being a middle value in terms of rankings, it's less affected by extreme values than something like the arithmetic mean. Often people are slightly disparaging about statistics because they might say, on average, if Elon Musk walks in the room, on average, we're all billionaires. Well, that's the arithmetic mean, which is heavily affected by outliers because it gives each observation an equal weight. So you get the same weight as Elon Musk in that average. The median's slightly different, isn't it? If you imagine all ranking us by wealth, if Elon Musk walks in the room, it's a big queue. He goes to the front, presumably, and the middle person doesn't change very much. So less affected by extreme values. The income or the wealth of the middle person doesn't change very much. The middle person will shift a little bit, but it's unlikely that the value that the middle person takes is going to change very much at all. Let's move on to the mode, another measure of central tendency. Always think MO, most often. All right, so this is the observation that we're seeing the most in a data set. Now, for discrete data can take a finite number of observations, like your shoe size. It tends to be relatively discrete. Here in the UK, it's there's children's sizes, and then you can be sort of, you can be size 3, 4, 5, 6, 7. All right. Don't think you can have a shoe size of 0. But the crucial thing is that your observations are funneled into these discrete observations, a small number of them. And so it's very easy to observe a most often shoe size. It might be size 8. That's the most common shoe size. But what about if we measured feet in centimeters or millimeters or nanometers? That's more like continuous data, isn't it? Continuous data, we don't really have discrete single observations that happen more than once. We don't have individual observations that happen more than once. Each continuous observation, if you measured feet in nanometers, you'll get a different observation each time. So that's where we tend to throw observations into buckets or bins, as they're called. Like, for example, daily returns of an index in a certain time frame. You might throw them into buckets. You can see the most negative bucket here is -4 to -3% on a daily basis. And the most positive bucket is 2 to 3% on a daily basis. That'd be a very strong return, wouldn't it, on a day, sort of 2.5%. And we're throwing observations. Here's the frequency, day count, if you like, about 250 days. We're throwing them into bins. And the modal range here is 0 to 1. Most often we see a return of 0 to 1 for that FTSE index for that time frame. You can have more than one mode, it might be the case that we see two values most often because they see very frequently and they're both seeing the same amount, the most frequent amount. Trimodal, 3 items, and so on. You could even have no modes where all of the items are the same, so there's nothing that's more frequent than another. But most often you're going to see unimodal distributions. Not massively statistically useful, the mode, just be aware of its basic definition for the exam. Now, we've talked about central tendency. Now let's talk about the spread of data. If you rank your data from lowest to highest, one useful thing to do is to talk about a quantile. Quantile is telling you a value that a data takes when we are a certain specified percentage through observations. So often referred to more generally as just percentiles, okay? Through a distribution or through a range of values where we've ranked them from lowest to highest. Think about it that way. So for example, the 75th quantile would be 75% of the way through the data. That's also referred to as the third quartile, where one quartile is 25% of the data. We don't have to work in 25%, we can work in 10%, like deciles, for example. 60% of the data points are less than the 60th percentile. So from an exam perspective, you might be given some data. This is mirroring the sort of thing you see in the curriculum where we're being told about 5% bins here. So as we move through these bins with these ranges, we see cumulatively 5% of the distribution each time. So for example, between minus 3.83 and minus 1.59, we see 5% of the distribution. That means the 5th percentile for this distribution would be here, 1.59. To answer this question, what would be the first decile? Where have we seen 10% of the distribution? Well, that's when we've observed cumulatively 10% of returns, and that's where we've gone through this bin, which is 5%, and this bin, which is 5% as well. So at a return of minus 1.01, at that value, we know that 10% of daily returns have been observed, less than 1.01% negative, all right? What about the first quartile? First quartile is 25% of the way through the data. So that will be observed when we're at the top end of the range. That it's the 5th bin. If each bin is 5%, at the top end of the 5th bin, we will have observed 25% of the data. So the 25th percentile is that 0.37% there. Incidentally, these columns are just showing you how many daily returns are in each bin. So it's about 5% of about 250, isn't it? 250 trading days in a year. All right, another way of representing data, quite specific this, but you might have seen this if you've looked at a basic stats class. To capture the dispersion of data, you kind of rank it vertically, and you can plot what's called a box and whisker chart, or box and whisker plot. So the box is here, obviously, and the box represents the interquartile range. In other words, how far we are from the 25th percentile, that would be the 25th percentile there, and the third quartile, that's what the interquartile range is. The interquartile range is the middle 50% of items, all right? So between the 25th percentile and the 75th percentile. So that gives you an idea of how clustered the data is around the middle. Median obviously will be in the middle. The arithmetic mean is, in this example, affected by outliers. You can see there's more big positive observations because this line extends further out here. The whiskers, by the way, are these lines with a kind of a gate at the end, and that represents the largest observation. So with a bit of positive skew here in the data, big observations, big outliers to the top, not outweighed by big outliers on the bottom, we can see that the mean's getting dragged up a little bit higher than the median. So this gives us an idea of where our data is clustered, how it's dispersed. 50% of it is in this range, that's the middle 50%, and then outside of that, kind of where your outliers lie, you can see there's some positive skew in this data here. You can adjust the box and whisker plot. Something that's very common is to put fences at 1.5 times the interquartile range so we can specifically observe outliers. So here you can see the fences are put at 1.5 times the interquartile range, all right, which is taking us out. Now, if that's the interquartile range, then 1.5 times that is taking us out here. And then we specifically look at the outliers. We specifically plot them on the box and whisker plot. This is not the same data as before. This is actually the FTSE data that we looked at, and you can see some negative skew here and some big negative outliers close to -4%, that -3.8%, as we saw before when we were looking at the bins. All right, so the idea here is, it seems like a rather arbitrary figure, but this is just common practice, if you like. 1.5 times the interquartile range sets where we put our fences here, where our whiskers essentially end, and then we can actually individually observe these outliers. We can see there's more outliers on the downside with this FTSE data, and they tend to be more widely spread, which is very, it's very important when you're thinking about potential losses, because your losses are down here on the negative side. Okay, just be aware of what you're looking at there and be able to interpret that for the exam. Okay, so we're going to use some CFA Institute data to carry out some basic statistics in terms of their calculation. All right, so we've got here monthly returns. There of course is 12 of these. So if anyone asks you about sample size, 12 months in a year, that would be your N. Okay, we're going to be looking at the dispersion of this data. First up, the lowest one is -4 and the highest one is +6. So if you're thinking about dispersion, how broadly dispersed this data is, I think the crudest measure would just be to look at that range. The highest data point was 6% and the lowest was -4, and so the range is 10%, 6 minus 4. Another measure that's commonly used is mean absolute deviation, or MAD. The mean absolute deviation is quite a simple measure. It's really looking at your average distance. So what we mean by absolute. Absolute means we're looking at size rather than sign. Now remember, we're trying to get a measure of dispersion of the data here. So it's tempting, by the way, to sort of have your mean for the data, which the sample mean, by the way, gets represented as X bar, where X, or it might be R bar if you're looking at returns, X bar more generally for general data X. So there's your arithmetic mean in the center of the data. You might be tempted to just say, well, let's look at our observations, X1, X2, X3, and so on, and see what the average deviation is, where the deviation is distance from the mean. The problem with that is, due to the nature of the arithmetic mean, if you do that and you add up those deviations, the negatives will cancel out with the positives. So the average deviation when you reflect signs, they're positive, they're negative, would actually be 0. So we can't take average deviation. So that's why we take the average absolute deviation, the mathematical symbol for absolute, the absolute function, just looking at the size of something and ignoring the sign of these vertical lines. And so really we turn these negatives positive and think about the distance, the size of the distance rather than the sign. So the first thing you do to get this MAD out is you calculate the mean in the middle of the data. Now hopefully that's not too much of a stretch. You can just add those numbers up and divide by 12. Okay, so that comes out at 2.25. All right, so that's the mean of the data. The arithmetic mean sitting in the middle, sitting in the center of the data there. When we think about deviation, our deviations are relatively straightforward. Our first return was 5. That is, when we think about how far away that is from 2.25, the mean, we get 2.75, and so on, right? So the rest of this data is really, these columns is really just taking spot 25 off of the number, right? And you're getting the deviation. But if you add those up, you will get 0. All right, so what you're going to do is you're going to think about size instead of sign. So just drop the signs, all right? That's step 3 here. Drop the signs and just add them all up and divide by 12, and that will get you to your average absolute deviation. So the MAD here turns out to be 28.5 over 12, which is 2.375. So that's a dispersion measure, okay? Now, it's quite compelling to use MAD, and a lot of people say, why don't we use that all the time? Because we don't use it all the time. Now, the reason really is it's not a very useful function from a mathematician's point of view. Whenever you see this sort of absolute sign and we're just making negative numbers positive, that doesn't bode well for thinking about rates of change and things like that. Mathematicians kind of start saying, well, that's not going to be continuous, or it's not going to have a slope, at certain times. So mathematicians don't dig that. So what measure of dispersion do mathematicians find useful and that they can then use in their kind of calculus when they're looking at statistics? The answer to that actually is variance. So variance is an approach where our aim is to remove the negative signs, but instead of just taking that absolute function, which is not useful, we just square deviations and look at the average squared deviation. Okay. Now this formula is quite ugly and often intimidates people. So let's remember what we're actually doing here. We've got some data points. We know that their mean sits in the center here. All right, there's like an x1 over here, which has got a negative deviation. You're just calculating that distance, right? x1 minus x bar, and then you're squaring it. For the next data point, say x2, you're going to calculate this distance, x2 minus x bar, and you're squaring it. You're adding up those squared deviations across all your data points, all right, and then you're dividing through effectively by the number of observations. You've got to be careful with that though, because need to qualify that. You would be forgiven for thinking when I say then you divide through by the number of observations, you would be forgiven for thinking that we divide through by n, but we don't, and that's why it's in red here. You've got to be careful with that. If you're looking at a sample, which we are, this here on the top represents the sum, so that's a summation sign, sum of your squared deviations, right? That's on the top. To take an average, you would usually divide by the number that you've seen, but look at this. You're actually dividing by n minus 1 here. So what's going on there? Well, we've got n data points, but we've only divided through by n minus 1. So what's going on? Well, a mathematician would wander in and say, I can talk about this for a long time. And you sort of go, I don't really want you to talk about it for a long time. Just try and explain very quickly why we're only dividing by sample size minus 1 there instead of n. And the mathematician will struggle, but they might say something like, well, you've used the sample mean in the calculation of your sample variance. Yeah? Right. Well, by fixing this sample mean, which itself should be free to be whatever it wants, because you could take any sample, what you've done is you've lost what's called a degree of freedom. And what that means is one of your data points is no longer free to be whatever it wants. Right? All of your data points up to the last one can be whatever they want when we observe them, apart from the last one that needs to take the value such that we get the x bar that we're fixing in our analysis. All right. So think about it like this: one of your data points, one of your x data points, xi if you like, is not free. It's not random anymore. It's actually defined by the other data points. Whatever you've observed up to the n minus 1th item tells you what the nth one must be, so that's not free anymore. You've lost a degree of freedom. So the mathematician says that quickly, you kind of go, right, okay, so if I just remember for a sample variance that we divide by n minus 1, not n, that's a big, crucial kind of banana skin that we need to be aware of, then you know what you need to know, and the answer to that is yes, okay? If it were the population, in the unlikely event we're looking at all items in a population, which we never are, because statistics is all about taking samples. But in the unlikely event that we look at all members of a population, then yes, you would divide by n, where n is the big N, is the number of observations in the whole population. But we never are. In statistics, we're always looking at samples. And when you look at samples, you're not really looking at the true population variance. And by the way, you do need to make that distinction, right? The true population variance, often unobservable for practical reasons, that would get the letter sigma squared, right? The Greek letter, the true population parameter. And that thing exists and is a fixed number. But however, your sample variance depends on the sample, all right? And your sample variance has not got all of its data points freely taking whatever value they wish. They're not all random. So there aren't n sources of variance, really. There's only n minus 1 sources of variance, right? Degrees of freedom, as they call it. Okay? If you did the true population, divide by the number of observations in the true population. For a sample, though, divide by n minus 1. That's what you need to know. Okay, by the way, this squared deviation is in squared units. So if we started off in percent for returns, we're now looking at percent squared, which doesn't make any sense. So let's square root it back down, and we get back to the square root of s squared is s, and it turns out that s stands for standard deviation. Okay, now s tells you it's based on a sample. If you were looking at a population standard deviation, then you'd be looking at sigma, which is the square root of sigma squared. Okay, but like I say, in statistics, almost all the time you're looking at samples and you're thinking, what does that mean for population parameters? And therefore we're looking at s squared, calculating it as such, taking the square root to get back to a sample standard deviation. So let's think about how you would do that for the data that we're using. There's the data again. All right, you know that the mean that we calculated earlier is 2.25%. All right, so there's your deviations, same as before, by the way. Those deviations are exactly the same as before. 5 minus 2.25 is 275. 3 minus 2.25 is 0.75, and so on. And all you're going to do is square this column here to get the final column. You can see the negatives go away, and then you can add up these squared deviations. All right, they add up to 96.25. That is the numerator of your sample variance. Okay, so if you want to get to sample standard deviation, you can take that 96.25, divide by n, where n is 12 minus 1. 96.25 divided by 11, 12 minus 1 is 11, gets you to about 9-ish. Take the square root of 9, about 9-ish, and you'll get about 3-ish, 2.958%. Okay. Now there's a box here which says much quicker on the BA2 Plus. I'm actually loath to use the BA2 Plus here. It can do it, but if you rely on the calculator and you don't understand what you're doing, you leave yourself open to qualitative questions which test your understanding, which is what the CFA is all about. So if the examiner asks you, is variance based on average cube deviation? If the examiner asks you, what's the difference between calculating a population variance and a sample variance? What's the adjustment? Is it to the denominator and the numerator? These sort of things you've got no hope if you're just relying on the calculator. The other thing is the calculator isn't actually really a shortcut. And the other thing is the examiner is unlikely to ask you to go through this perfunctory calculation like this. It's in the curriculum, sure, but in the exam, are they going to reward you for being able to tap, 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 tappity, tap, tap, tap? That's not what the game is. That's not what the game is. People who this is a bit of a false idol, this thing. People put too much faith in this doing the thinking for them in the exam. This doesn't do any thinking. You do the thinking. This just does some heavy lifting. And I'm not sure it even does much heavy lifting in this case. However, having said all of that, I know that people will want to see it in action. So let's see it in action here. Let's see if we can do it quickly. For those of you that are not interested, feel free to skip this bit. But what we're going to do is we're going to go second 7 to open up a data worksheet. Clear it. So second CEC clears it. And then I'm going to make my X terms the data. So my X terms are going to become my X terms. So for example, X01, I'm going to hit 5, enter. Right? Now I arrow down twice because there's no Y variable. 3 is going to be 0, X02, right? So 3, and so on. X03 is going to be -1, so 1, and then turn it negative, enter. Arrow down a couple of times. X04 is going to be -4, and so on, right? So just bear with me as we do. X05 is 4, all right, and X06 is 2. That's only half of it. We've got X07 is going to be 0, and X08 is going to be 4. I'm hearing myself in that sped up voice now. X09 is 3. X10 is 0. X11 is 6. We're ignoring the Y's because there's only one data set. All right, X12 is 5. Right, that's you input in the data. To analyze it, you go to the stats worksheet, second 8. The mode you want to be in is 1-V. There's plenty of other modes like LIN. You can toggle through them by going second enter, changing the setting. LIN, LN, EXP, power. You want to be in 1-V. That's the mode you want to be in. Once you're there, arrow down, tells you there's 10 data points. Your mean is 2.25. We knew that. And arrow down again. There you go. your sample standard deviation is 2.958. So, if you care about that, then that's great. But my advice is try and understand what you're doing. And I don't think the examiner is going to ask you to do a standard deviation with like 12 calculations in it. But they are going to expect you to know what's being done. Okay. All right. Moving on now. Standard deviation. What is it? It is actually your average expected deviation from a mean. So it's telling you how far on average you expect to be away from a mean. It's giving you a measure of dispersion. Now, one of the problems with standard deviation is that it is used as a measure for risk. So sample standard deviation is S, and it's used as a proxy for risk because it's telling you how far to the left you could be, but it's also telling you how far to the right you could be as well. So as my old boss used to say, is it good volatility or is it bad volatility? Volatility is another name for standard deviation, right? Yeah, but is it good vol or bad vol? My boss used to say, and I didn't used to think he had a point, but I now do think he does have a point. This is a lot more damaging than that, right? So there are measures that focus on the left-hand side of the distribution, what's called target downside deviation or target semi-deviation, okay? Here, we're only going to consider squared deviations when we are below a target that's specified by the analyst, by the user, by you, right? So B is like a barrier or like a sort of a threshold. And we're only going to consider squared deviations when we're to the left of that. We're not going to consider squared deviations when we're actually beating that threshold, okay? Notice we're still dividing by n-1, where n is the full sample size. We're only considering squared deviations below the target, essentially, the barrier or the target, okay? Let's have a look at that applied to our data when we've got a target or a barrier, if you like, B for barrier, of 3. So what that means is we're only really interested in squared deviations when we're below 3. So we can ignore 5, we can ignore 3, we can ignore 4, 4, 6 and 5. We can ignore them. We can also ignore that 3 as well to be consistent, all right? We don't need, you could ignore them or you could throw it in and get a deviation of 0, okay? What we're interested in is the deviations, squared deviations below 3. All right, so it's not the mean anymore, it's the barrier or the target, right? So obviously -1, -3 is -4, -4 minus 3 is -7, and so on. So these are the things we're going to add. 16 plus 49 is 65, 66, and then we've squared them, by the way, of course. Squared that, -4 squared is 16, right? -7 squared is 49. So we get 65, 66, 75, we get 84, if I do that in my head, and I've done it right in my head. And now we can take that 84 as the numerator. That's all that's changing really is the numerator. Divide by n-1 and then take the square root and we'll get 2.763. What's the point here? I hear you scream quietly. The point is that actually we're punishing for downside squared deviation, right? And so any investment that's got negative skew and big outliers to the left of this target will be punished and look very risky, have a high downside deviation, okay? All right, let's have a look at a measure now which combines standard deviation and the mean return. Don't forget the mean, sample mean x bar is often used as our reward, what we expect going forward on average, and S is often viewed as risk, how far to the left of our reward we could be on average, right? And to the right as well. But if we're going to combine these two, we might divide risk by return and look at the coefficient of variation. How much risk is there per unit of return? Obviously, we want this to be low because it means we're taking low risk per unit of return that we're expecting. So based on this one naive measure, you would go for the lowest coefficient of variation. Have a look at these two assets here. If you've got asset A with a standard deviation of 10 and a mean of 5, that's got a coefficient of variation of 10 over 5, which is 2. When you consider that next to asset B, which has a coefficient of variation of 12 divided by 8, you find this lower coefficient of variation will be more attractive. Now, like I say, it's quite a naive measure. It's quite simplistic, but based on that measure alone, you would prefer asset B because there's less risk per unit of return. Now, up till now, we've only considered what are called the first two moments of a distribution, the mean, the expected value, which is the mean, and the standard deviation, like the which is based on the squared deviation from the mean. It's based on variance. We do have measures which are based on cubed deviation, and we do have measures which are based on deviation to the power of 4, and they're called the higher moments of a distribution. So let's deal with the cubed one first. The cubed one, cubed deviation, looking at a measure that's based on how far you expect to be away from a mean cubed. If you think about it, when you cube negative numbers, they become bigger and negative. And if they're big negatives, they become bigger and negative. And if you cube positive numbers, they become bigger and positive. So this is how we get a measure of lack of symmetry. Because if there's more big negative things than big positive things, that will come through with this negative skewness that we calculate based on cube deviation. All right. So if a distribution lacks symmetry, then you will see that through negative skew, or positive skew, right? If we lack symmetry, we're actually worried. We'll look at some pictures in a moment, but we're actually worried about negative skew because that would mean there's bigger negative outliers to the left of the mean, which are losses, than there are big positive outliers to the right of the mean. So a symmetrical distribution, of course, has zero skew. We refer to here the normal distribution. That is a symmetrical distribution. The normal distribution is a very commonly assumed distribution in statistics. It's pictured here. It's a nice kind of perfect symmetrical bell shape. It's often called the bell curve. It has got quite a complex mathematical formula which defines it, but we don't need to worry about that for CFA 1. All we need to really appreciate is that there's a very commonly used distribution out there called the normal distribution, and it is symmetrical. In other words, outliers to the left of the mean have the same frequency and size as outliers to the right of the mean. All right, you get the same shape of the distribution either side of the mean. Often we start talking about distributions without defining our axes here. You can think at the moment that we're talking about values, say returns, things like that, and the vertical axis of the distribution is really telling you about the likelihood of observing a value there. Mathematically, it's a bit more complex than that, but it's good enough at the moment to just think the vertical axis, when this chart is high, you're very likely to see a value there, and when the chart is low, you're not so likely to see a value there, right? So think of it as like a likelihood function, very similar to that kind of what's called a histogram of frequencies observed that we saw earlier on. Now, with a symmetrical distribution here, the point that's being made is that your arithmetic mean is the same as your middle value, your median, which is the same as the thing that's observed most often, right? Your mode. Your mode is at the top, the peak of the distribution. It's what you're most likely to see. Median is in the middle, but the middle is perfectly the same as the arithmetic mean, which is in the middle if you've got a symmetrical distribution. So what does a lack of symmetry look like? Well, positive skew means you've got a longer right tail. It means you've got big but infrequent large outliers on the right. That's actually a good thing from a returns perspective, because that's like winning the lottery. Very unlikely, but a very big impact when it happens. We're actually more worried about negative skew, which is where there are big negative returns, big negative returns with a low probability, low frequency, if you like. All right. So we don't like them. We don't like negative skew because that means there's a bullet in the chamber. Things could go very wrong. It's not very likely if there's lots of chambers, but things, when it comes up, we could suffer significant losses. Like a sort of a tail event, a big sort of crisis could be quite heavy here. Negative skew actually, rather unfortunately, from an empirical perspective, most asset classes exhibit negative skew. Stocks do, and particularly credit. Lending money to people, most people pay it back, but every now and then someone defaults and you lose a lot of money. That's a very negatively skewed distribution, isn't it? Most people pay their loans back, all right, and every now and then you get a big default. Very negatively skewed distribution, credit-wise. All right, just be aware that the different measures of central tendency are affected differently by skewness. It's the mean, we said earlier, that's most sensitive to outliers, so that gets dragged along. If Elon Musk walks in the room, right, that gets dragged along the most. The middle item, not so much. By the way, the mode doesn't get affected at all. The thing that you observe most often, the peak of that distribution, isn't affected at all by an outlier walking into the room. The mean would be dragged to the left the most by negative outliers when there's negative skew. Okay, on to the fourth moment of a distribution, which is based on deviation to the power of 4. Now, if you think about it, when you power something up by 4 times, the sign is removed, a bit like when you square it. But really big things get exaggerated to be super big, and really small things get exaggerated to be super small. So what we're looking at here with regards to the fourth moment of a distribution, referred to as kurtosis, we're really looking at the shape of a distribution, all right, how the shape plays out, all right, and our benchmark really is the normal distribution. Turns out the normal distribution, when you calculate its kurtosis, which you don't need to do, I should point out, you don't need to calculate skewness or kurtosis for CFA1, but when you look at a normal distribution, that has a kurtosis when you calculate it of 3, all right, so a normal distribution has a kurtosis equal to 3. That's a very important thing that you need to know right off the bat here. All right. So actually, if you've got kurtosis greater than 3, then you are said to be of high kurtosis, and the formal name for that is leptokurtic or leptokurtosis. And I mention, it's a comment about the shape of the distribution. Well, leptokurtosis is where you've got a higher peak, more peaked distribution and fatter tails. See that coming in with that dark blue line there. And this is the concern. As far as investors are concerned, as far as we're concerned, as statisticians, we're worried about high kurtosis because it leads to bigger outliers on both sides, admittedly, of the distribution. Should be perfectly symmetrical, this. All right, it's skewness that deals with a lack of symmetry, remember, not kurtosis. But with kurtosis, we don't like high kurtosis because there's more chance of a big loss, right? There's also more chance of being close to the mean and less chance of a medium-sized deviation from the mean, okay? So we don't like high kurtosis. And once again, unfortunately, high kurtosis is a feature of most financial asset classes. If high kurtosis, which is a kurtosis of greater than 3, is what we call it is referred to as leptokurtic, then it does beg the question, doesn't it? What does normal kurtosis, a kurtosis of 3, get called? That gets called mesokurtic. All right, mesokurtic if you've got normal kurtosis. And it does also beg the question, if you've got kurtosis less than 3, what are you referred to? Well, that's referred to as platykurtic. All right, platykurtic, what would that look like? Well, a platykurtic distribution would have thinner tails and would be more domed, less peaked and more domed than a normal distribution. All right, so don't shoot me for the drawing here, but you can see the tails go to 0 quicker, should be symmetrical, of course. All right, and it's more sort of domed. That is a platykurtic distribution where the kurtosis is less than 3, less than a normal distribution. I always think it looks like a bit like a duckbill, and then I think of a duck-billed platypus, and suddenly we have our little memory trick to help us deal with all this Greek. It's Greek, this platykurtic meso discussion. There's a little table to sum up what we've just said. And by the way, we know that the kurtosis of a normal distribution is 3. We know that, and that's formally referred to as mesokurtic. All right, that's the middle here. And we know that greater than 3 is lepto and less than 3 is platy. All right, but just be aware there's this idea of excess kurtosis as well. Just be careful with that. Just the word excess can turn everything on its head, right? Excess kurtosis is kurtosis minus 3, because of course we're talking here with excess kurtosis about kurtosis relative to the normal distribution. So you've got to know whether that word excess is there or not, right? Because a kurtosis of 1 is platykurtic, isn't it? But an excess kurtosis of 1 is actually leptokurtic. So be very, very careful with that. It might be worth just revisiting our data to see how skewness and kurtosis, sample skewness and kurtosis, is represented in our FTSE data. You'll remember that the bins that we set up, you could see some slight negative skew there, couldn't you? And that's borne out when we calculate. You won't have to do that calculation, but that's borne out by that statistic there. Kurtosis-wise, actually, the data is relatively normal, even slightly low kurtosis for that particular data set. Okay, the average daily return was 0.01, very, very small, and you can see how the sample standard deviation dominates your returns in the short term here. You can see how much of a bigger deal risk is than returns when it comes to basic statistics. Okay, up till now, we've only been considering one data set on its own. There's been X, the X values, and we've been considering them on their own. We also want to think about how data varies alongside other variables as well, like how stock behaves relative to the market, for example. So this is where things like covariance come in. All right, covariance, there's a formula here, but we'll use it later. We're going to use it in a later module. We won't use it right here. Just appreciate what this is telling us. Covariance is telling us how far away two variables are together from their means at the same time. So if you imagine, this is where things like what are called scatter plots pop up. You've got two dimensions here. You've got the x axis, the y axis. Imagine if you had an observation there. It might be returns. The x might be the stock market, y might be an individual stock. All right, so there was a month here where the stock market's up, right, and the stock is up as well. That's great. It's getting quite busy, that picture already. So let's just get rid of that. So that's fine. If you plot lots of months, then you'll get something like this. You'll get like a cloud of data. Usually we're up, every now and then we're down, and so on. But there seems to be a relationship here. Now, what covariance will do is help you to establish what this relationship is. Now, what the covariance is really doing, just to kind of get behind it a little bit, is it will calculate your average y. That's what y bar is. Now, where is y bar? It's about here, isn't it? All right, there's y bar, the average y, the average sort of vertical height. Okay, and then maybe x bar would be about here. All right, so it's like another set of axes. What covariance is really doing is it's saying, okay, on average, are we both above our means together? If we are, then both of these will be positive, and that will add to covariance, right? That's that quadrant there, quadrant 1, I'll call it, right? Or are we both below our means together? If they're both below their means together, then we're in quadrant 2 here, and that means two negatives multiply together to get a positive. So we're multiplying these together, adding them up, there's the summation sign again. And if broadly speaking, which is the case here with my data, if broadly speaking your data is in these quadrants, then you'll find that covariance will be very strong and positive. If we see too many observations in quadrants 3 and 4, where in quadrant 3 x is below its mean, all right, so in quadrant 3 x is below its mean and y is above it, that would give a negative when you multiply them together. And quadrant 4 here, we've got x above its mean but y is below it, all right, and that will give a negative. If there's lots of observations in these quadrants, then actually you'll get a negative covariance. So look, I wouldn't worry about using this formula at the time being. Just be aware that we're looking at how far data points are away from means on average, and if they're the same side of their means together, on average you'll get a positive covariance. We're dividing by n-1 again, just like we did with a sample variance. It's the same with a sample covariance for the same similar statistical regions. Now, the problem with covariance is you can calculate it and look at it. It might be 65. Is that big or not? We don't know. Covariance can take any value. So a problem that we have with it, and we will calculate it in a later module, but the problem we have is like we don't really know if 60, say it comes out at 65. What does that mean? Don't know. That could be tiny if the underlying units are billions. It could be huge if the underlying units are just a few, a few dozen. So we don't really know where covariance is. All right, we don't really know. I mean, if it's positive, we know that positives outweigh negatives, so the variables broadly move in line together. If it's negative, we know that broadly the variables tend to move in opposite directions, but we can't really ever say how strong a relationship is. And also the units are based on squares as well. So there are two problems with covariance. So one of the things we like to do is standardize covariance. Notice how it gets the letter SXY. S was standard deviation before, all right, but that's now covariance. One of the things we like to do is standardize covariance. The way you standardize covariance is you take your covariance and you divide through by the product of the standard deviation. So divide through by the standard deviation of the x variable and divide through by the standard deviation of the y variable. So if, for example, you're told there's a covariance of 0.0046, seems to be rather coming out the ether, but if you're told that's the covariance of two data sets, all right, and then you're told that the standard deviation of x is this and the standard deviation of y is that, then it's nothing more sinister to take that covariance and divide through by the product of the standard deviations. For me, the easiest way to do this on the calculator is to just go, let's get out of there, shall we? So we can just go 0.0046, and when you've got stuff being multiplied, apologies, 0.0046, when you've got stuff being multiplied on the denominator there, you can just divide by 0.0623, okay, and then you can divide again by 0.0991. That's the quickest way of going about it, all right, and that's how you get the answer. So you can think I'm dividing by that and I'm dividing by that as well, okay. Now this is called correlation, all right, and this is a very important metric which you're going to be using all the way through your CFA program. That was 1, 2, and 3. Correlation is standardized covariance, and the really useful thing about it is correlation sits between +1 and -1. It can't be bigger than +1, can't be smaller than -1. So it tells us how, when you calculate it, you can see how big a number is. That is big and positive. That's like here, that's very big and positive. So you can deduce that, you know that now. That there didn't look like very interesting at all, but it turns out, given the volatility of x and the volatility of y, the standard deviations of x and y, it turns out that's very big indeed. That's a very big covariance indeed. Just be aware that correlation is measuring the strength of a linear relationship, a straight line relationship. Now, you've got to be really careful with that, because we're assuming that the relationship between these two variables is a straight line. It's telling us, it's not a great line of best fit I've drawn there, it's telling us how good a job that straight line is doing at explaining the relationship between those two variables. More on this in regression later on. But be careful. If you've got zero correlation, it doesn't mean that there's no relationship. It just means there's no linear relationship. Okay. If you've got zero correlation, there could still be a non-linear relationship between x and y, right? If you had data points like this, there's clearly some sort of sine wave going on, all right? But that's not a linear relationship. That might be a very low correlation, but you could model it in a slightly different way. The other thing is you might find correlation between two variables, and it might be spurious correlation. It could be very well the case that just you found a random artifact of data, and it just so happens things look like they move together, but there's no reason for it at all. You've just found an artifact of data, which happens. It's just noise. The other thing is that you might find a relationship between two data sets, but actually they're being driven by a third variable. That would be spurious correlation as well. You might think that eating an ice cream causes you to purchase swimming trunks, right? Of course, really it's the seasons that are driving the purchasing of swimming costumes, swimming trunks, bathing shorts, whatever you call them, right? It's their weather that's driving it. It's not that being stung by a bee means you go out and buy a swimming costume, right? That's not how it works. That's spurious correlation. You also get spurious correlation if you transform variables, or you could get spurious correlation if you transform variables, like there might be no relationship between the assets of a company and the dividend that it pays, but if you adjust for market value, suddenly there might look like there's a relationship when there isn't in the underlying data, for example. The curriculum doesn't go into a lot more detail about that, but just be aware there's 3 causes of spurious correlation: just random noise, a third variable driving it, or you performing some sort of mathematical operation on the data to make it look like there's a relationship, whereas if you undid the operation, it would not actually be there. Okay. All right, well look, that wraps up module 3 masterclass video. Make sure you can do all the calculations that we did in this video and you can move on.